Okay, welcome back, everybody. Hope you had a good weekend. Got plenty of candy yesterday. Anyway, just no announcement really to make other than we are on chapter 13, which is reasonably short, kind of short, not like the others that we've done in the past. Not as short as the one we just finished with thermodynamics, but that shouldn't take us long to knock this one out. Probably if we do finish early, I'll just stop it here. Chapter 14 is a little bit longer, about 36 slides. And then chapter 15 is back to another short one. So the point being that we're basically, catching up with finishing up all of the chapters, which means that toward the end of the semester, we probably will have at least a couple, if not more, sessions that are open for you here. And so, I'll be here. We won't have lecture, but they're open, treat them as an office hour. I'll be here the whole time, open to any questions or so forth. So you might start preparing for that, start, writing down questions at any of the chapters that you want to have any questions about. And get you ready for the final exam, which is comprehensive, covers all the chapters. Okay. All right. So let us begin with chapter 13. Okay. Now, this particular chapter is called stoichiometry. And basically is the relationship between reactants and products, which is what we've been doing in the past. What I've been telling you about every time we balance an equation, I said, hey, take a look at the reactants, look at that, the coefficient, look at that ratio between reactant A and reactant B. And sometimes it was a straightforward 1-to-1, sometimes it was a 2-to-3, 4-to-6, whatever it may be. Whatever you did to balance, whatever coefficients you use to balance, that is the stoichiometry of the reactants. Not only reactants amongst themselves, but of the products. What is the ratio of reactant A with one of the products or the other, if you got more than one product? And those are the coefficients that we need to make sure we have the proper coefficient, because with the concept of the mole, which we just talked about, when we take the grams of compound X, we convert that to moles of compound X. Then based on the stoichiometric relationship between, say, compound X and compound Y, that would then convert us into moles of compound Y. And then from the atomic mass or the molecular mass of Y, which is what we're looking for, we can calculate the number of grams. But to get to point A to point B, like we did in the last chapter, we have to go through moles, okay? So let's talk about the stoichiometry. Let's say, for example, we have this equation where we have nitrogen monoxide, okay, reacting with oxygen to give us nitrogen dioxide. And so after it's balanced, we see that we have two nitrogen monoxide molecules, one oxygen, and then two of the nitrogen dioxide. So after it's balanced, the coefficients tell us that we can, I've been using the term molecules. 2 molecules of NO require 1 molecule of oxygen to give us 2 molecules of the product, nitrogen dioxide. Now, we may have more than just 2 molecules. We could have 10 molecules. No problem, because that ratio of 2-to-1 between NO and oxygen remains the same. So if we use 10 molecules of NO, then we need at the minimum 5 molecules of oxygen, because that ratio is still a 2-to-1 ratio, which then in turn will give us 10 molecules of the product, okay? Now, we don't really work with or deal with molecules, so we use the term moles. And so instead of calling it molecules, we go with 2 moles of nitrogen monoxide, okay, plus 1 mole of oxygen, react to give us 2 moles of nitrogen dioxide. And remember that 1 mole is 6.02 times 10 to the 23rd molecules. Okay. All right. So the relationship, the stoichiometric relationship between NO and oxygen is a 2-to-1. So we have a ratio here that we can write with NO in the numerator and 1 oxygen in the denominator, or inverted, okay? And that relates between the 2 reactants, but we can also find the relationship between, say, oxygen and the product. And that is 1 O oxygen to 2 nitrogen dioxide, which you write in that manner, or just simply inverted, okay? Which one we utilize depends on the question being asked, okay? And just like we did before with respect to converting units, remember that exercise we did in the beginning where we had, for example, 1 inch was equal to 2.54 centimeters. That was our relationship, right? And we can write that either with centimeters in numerator or in the denominator, simply inverted. Okay, that factor labeled method we'll be utilizing here, okay? But in order for this to be correct, as far as the calculations, we have to make sure that we balance it properly, okay? Because you can see here that that ratio between nitrogen monoxide and oxygen is 2-to-1. And if we inadvertently balance it and say, you know, this is a 1 here, and when we do our calculation, you know, it won't be incorrect because that ratio is not correct. And that ratio is not correct because it wasn't balanced properly. Okay. So ultimately, where we're going with this is this. We could say, all right, if I have 10 grams of nitrogen monoxide, how many grams of nitrogen dioxide are we going to make? Okay, and so the relationship here, the question is simply between NO and NO2. And so what we may need to know is the molecular mass, the atomic mass for nitrogen monoxide and the product. We need to know the stoichiometric relationship between NO and N2O, which is 2-to-2 or a 1-to-1 relationship. And that allows us to go from point A to point B, okay? All right. The next one is we have here nitrogen in the presence of hydrogen reacts to give us ammonia. So 1 mole of nitrogen requires 3 moles of hydrogen gas, okay, which react to give us 2 moles of ammonia. Note the relationship between reactants, and so 1 to 3. Note the relationship, as I stated, 1 to 3 here. And then from nitrogen to ammonia is a 1 to 2. So this is a 1 to 3 here. This is a 1 to 2 relationship. From hydrogen to ammonia is a 3-to-2 mole ratio, okay? Or I said 3-to-2 because I'm going from hydrogen to ammonia, but I could be going from ammonia to hydrogen, so that would just invert 2-to-3 or invert the relationship. Okay. All right. So the coefficients which come from the balance chemical equation gives us these mole ratios that we need to use in our calculation. So, for example, we have here iron 3 oxide reacts, 1 mole of iron 3 oxide reacts with 3 moles of carbon monoxide to give us 2 moles of iron and 3 moles of carbon dioxide, okay? And then just looking at the relationship between reactants, we have this mole ratio, okay? 1/3, one iron 3 oxide over 3 carbon monoxide, or vice versa. And then this relationship, this one here, is the relationship between the iron and the carbon monoxide. And don't forget, you have a total of this relationship here, that's 1. And then you have this one, that's 2, 3 relationships, 4 is here, 5, and then between the products, 6 different mole ratios that you have to work with here. And which one you use depends on the question asked. So let's take a look at, let me fix that. Okay. So question answers, how many moles of iron can be formed if we have 10.02 moles of carbon monoxide, okay? So the key here is to make sure, read the question carefully, see which are the reagents or compounds that we're working with. So iron, we're dealing with iron and carbon monoxide, okay? So we're just dealing with the relationship between iron and carbon monoxide. We don't care what's going on with the other species, okay? Our simple goal is looking at the relationship between iron and carbon monoxide. So if we start off with 10.5 moles of carbon monoxide, what do? We, like any of the problems we've been doing before, we write down what we have, what we're given, we write down the units that we're looking for, and then we're going to have a ratio in the middle to get us to those units. And so we have 10.2 moles of carbon monoxide, okay? We're going to have something here, and we're looking for moles of iron, right? And so our relationship is between iron and carbon monoxide based on the balanced chemical equation. And so obviously we want carbon monoxide in the denominator, right? Because when we multiply this through, we want carbon monoxide to cancel. And we want iron to be in the numerator because those are the units that we're looking for. And don't forget to plug in the relationship. So the relationship is 2 to 3, okay? That ratio, which again comes from the balanced chemical equation. So if you look at the way this problem is set up, you're starting off with moles of carbon monoxide, then now you are going over to moles of iron, okay? And to get from point A to point B, you have to find a relationship that relates the carbon monoxide to iron, which comes from the balanced chemical reaction, okay? Note that we're dealing with moles, but you can take one step back. You start with grams of carbon monoxide, convert that to moles of carbon monoxide, using the ratio from the balanced chemical equation, convert that to moles of iron, and having the atomic weight of iron go to grams of iron. But right now we're going to just start with the moles, and the grams come in here in a bit. Okay, so there's our relationship. Double check that our carbon monoxide cancels. Iron is left because that is what we're looking for. All right, now the question is, how many moles of iron 3 oxide are needed to form 17 moles of carbon dioxide? Okay, so let's look through the balanced chemical equation. we are concerned about the carbon dioxide and the iron 3 oxide. Okay, so what's happening in here, no concern, just between carbon dioxide and iron 3 oxide. If we have 17 moles, and what I do is I write down the balance equation, what I'm looking for. If I need to make 17 moles of carbon dioxide, how many moles of iron 3 oxide do I need to begin with, is the question, okay? And this is a type of question now that is utilized not only in the lab scale, but even in the industrial scale. It's the same reaction if I were to run this in a lab, or if I had a big giant chemical plant where I'm trying to run this reaction for whatever reason, but I'm making carbon dioxide and iron from rust, which is basically the iron 3 oxide, okay? And so it's the same process, except obviously in the industrial plant, we'll be working with just, tons of this material. But the basic chemical reaction and the calculation is the same. All right, so let me rehash here. From the question, identify which normally we're only dealing with the two species, what we're looking for and what we're given, okay? And so we're given the fact that we need to make 17 moles of carbon dioxide, and we need to figure out how much iron we need to make. So I identify that in the equation, and I just erase the others because they're not involved in the question. They are involved in the reaction, but not in the question, okay? So with that in mind, then we just plug in the information of what we are given. 17 moles of carbon dioxide, okay? We are looking for moles of iron 3 oxide. And so our balanced chemical equation needs carbon dioxide in the denominator and iron 3 oxide in the numerator, right? And so carbon dioxide is 3, iron 3 oxide is 1. So it's a 1:3 ratio, okay? My carbon dioxides cancel out. My units of iron 3 oxide remain. I have it set up properly. Now it's up to you to do the math in your calculator. Okay, and it should come up with 5.7. Don't forget, I forgot to tell you, don't forget to keep track of your sig figs. These coefficients are obviously your whole numbers, they're exact numbers, and therefore would not be utilized in determining the sig figs. But moles comes from a measurement. So yes, moles would be moles of reactant or product or whatever you're trying to calculate, or come from a measurement. And so therefore they would be a factor in sig figs. All right, so it requires double check. You can see here CO2 cancels out. And so about a third of the 17 moles of carbon dioxide are needed, okay? All right, so here's an example. We have sulfur dioxide in the presence of oxygen are reacted to form sulfur trioxide. Okay, so obviously we can see it is not balanced. So if you're given the reaction, the first thing you got to do is you got to balance it. Now, this is one of the reactions that we are basically do a trial and error. And if we put a 2 in front of sulfur trioxide, that gives us 6 oxygens on the right-hand side, okay? And with that being the case, and plus 2 sulfurs go up. The sulfurs goes from 1 to 2, so we put a 2 in front of SO2. That gives us 2 sulfurs. That gives us a total of 6 oxygens on the left-hand side. 4 of them come from sulfur dioxide. 2 of them come from oxygen, okay? To give us 6 oxygens on the right-hand side. All right, so we have balance. Now the question is, how many moles of sulfur trioxide will form if we have 0.165 moles of oxygen? So what we're looking at is the relationship between oxygen and sulfur trioxide. Okay, and so I write it down so it kind of tells me what I'm doing in moles. Okay, and what I'm looking for is how many moles of this. Okay. All right, so I write down what I'm given, 0.165 moles of oxygen. Obviously, I'm going to have a conversion factor here, and I'm looking for moles of sulfur trioxide. So O2 is in the denominator and SO3 in the numerator. Okay, and so O2, there's 1, and SO3 is 2. Okay, so I'm going to need twice the amount of oxygen. Using 0.165 moles of oxygen should give me, oh, let me clear my mess here, 0.33 moles of sulfur trioxide. Okay, so what's happening here is not that we're not ignoring the other reactants, because the problems is the relationship between these two here. When that occurs, it's assumed that we're going to have enough of the sulfur dioxide to get this reaction to proceed. Okay, and that's why we can go basically ignore it. Okay, and we're just concerned about the species, the entities that the question asks for. All right, next one. How many moles of sulfur dioxide are needed to make 0.042 moles of sulfur trioxide? Okay, so we want sulfur trioxide and sulfur dioxide. That's the relationship. Now, if for whatever reason, if I need to make 0.042 moles of this material, sulfur trioxide, well, how many moles of sulfur dioxide do I need is the question. Okay, and look at my relationship. It's a 2-to-2 mole ratio, which is a 1-to-1, right? So right off the bat, without showing any work, I can see that I'm gonna generate the same amount of I'm gonna need the same amount of sulfur dioxide. So we write down what we're given. Okay, sulfur trioxide. Obviously, we have a conversion factor. We're looking for moles of sulfur dioxide. So we want the sulfur trioxide in the numerator, SO2 in the numerator, excuse me, SO3 in the denominator. Okay, and so it's a 2-to-2 relationship from the balanced chemical equation, which is essentially a 1-to-1, right? Because the 2's cancel out. And so we're going to need 0.042 moles of sulfur dioxide. Same amount. Okay. Check again, make sure your units cancel out properly, leaving us SO2, which is what we're looking for. And the rest is up to you as far as plugging the right number into the calculator. Okay. At this point, what we're doing is just calculating moles. Now, from moles, if you recall the what do you call it? The previous chapter, we can go from grams, and we'll do some examples. Okay. So also we can go from moles to the number of molecules using Avogadro's number. And if we were at STP, we can calculate and these are all gases, which they are, the volume at STP, right? And so here's the thing, from moles, we can get to grams. We can get to liters if we are at STP, okay? So from moles, we can go to grams, or we can get 2 liters, depending on the situation. And the question, I should say. All right, so this is part of the flow chart that we're going to put together for you. We're going to include what we did with STP in the molar volume, and we're going to include it with this one to give you one big flow chart that you can utilize for helping you through these equations or these calculations, okay? And so, and we start on the far left. If you're given a problem in grams, okay, well, with the molar mass, which is, recall, that is adding up all of the atoms involved in the formula, and the formula comes from our knowledge of how to put the formulas together, right? If they're ionic compounds, or if there are covalent compounds, given the name, we can figure out the formula, correct? So from the molar mass, we're going to take the grams given, divide by the molar mass, which is essentially inverting the molar mass, because the molar mass is in grams per mole units. Remember that. And so if you're going to moles, we're going to multiply with moles per gram, because you're given grams, you want to cancel the grams out, okay? And that gives us the moles that we're given. Now, from the balanced chemical equation, this is coming from the equation, or reaction equation, okay, that will get us to the moles that we're looking for. And if we have its molar mass, now it's grams per mole, we're multiplying those moles by the molar mass, okay? You can see where moles cancel. That gives us grams, okay? Point being, we can't do anything from apples to oranges unless we go through moles. I cannot go from grams given or whatever the species is to grams what I'm looking for. Can't do that unless I go through moles, okay? And I was trying to demonstrate here, when we're given grams, we are essentially dividing by the molar mass, okay, right here. And then when we find the moles, we're multiplying by the molar mass to give us grams. Okay, let's take this example here. We have iron 2 oxide reacting with aluminum. To give us iron plus aluminum oxide. Can anybody tell me what type of reaction this is? What type of reaction? These are good, these are good type of questions that where you could be given this reaction in words, and then asked you asked to first one, write the equation out, okay, from the wording, and then balance it, okay, and then maybe identify what type of reaction this is, and then from there be given problems of actually doing calculations. So, if iron 2 oxide in the presence of aluminum, we actually give you iron plus aluminum oxide, what type of reaction would this be? Double replacement? Not quite. Remember, double displacement, you have 99% of the time you have 2 aqueous reactants, both ionic compounds, and they exchange partners. And one of them may be insoluble, and you get a precipitate. You look at the products. So the double replacement wouldn't define this. What do you think it would be? I'll give you a hint. You need the activity series. Does that help you out? change the double to single replacement. Yeah. Okay, remember the activity series where you look at aluminum and iron and you figure out which is the most reactive metal? Well, aluminum is a lot more reactive than iron. Okay, and aluminum is not in ionic form, so therefore reaction proceeds. Okay, so this is an example of a replacement reaction, a single replacement. All right, so here, the question is two-part question. I'll go ahead and put them both out there, and the next page we'll break them up again. So what you're asked to do here is to calculate the mass of iron 2 oxide. Okay, calculate the mass of iron 2 oxide needed to react completely with 5.55 grams of aluminum. And so we're looking simply at the reactants, okay? And so if I start off with 5.55 grams of aluminum, question is how many grams of iron 2 oxide I need, okay? That's question number one. Question number two, and let me see, let me change the color a little bit, is asking, calculate the mass of aluminum oxide, which is this, okay, produce when 10.25 grams of aluminum. So we're looking at this relationship between aluminum and aluminum oxide when 10.25 grams of aluminum react, okay? So note the first in yellow, the relationship is a 3:2, and for the one in blue is a 2:1 relationship, okay? So calculating the mass of aluminum oxide. All right, so let's work the problem. All right, so the first one says, I have 5.5 grams of aluminum, okay? And we're going to figure out how much iron 2 oxide we need. So our relationship, what we're concerned about is the relationship between these two, okay? So we write down what we're given. Okay, I forgot to write down what we're looking for here. We are looking for grams of iron 2 oxide. Okay. All right, so the first step is to take the grams of aluminum and convert it to moles of aluminum. And we do that by dividing it by the atomic weight of aluminum. Okay. So look at the units. I cancel out at this point, unit-wise, I'm set at moles of aluminum, okay? The next now is I need to go and get into moles of iron 3 oxide. And I use the stoichiometric relationship between the aluminum and the aluminum iron 2 oxide, which comes from the balanced chemical equation. So keeping track of my units, you can see that moles of aluminum cancel out. So at this point, right here, you are to stop the calculation. I would be in units of moles of iron 2 oxide, which is not where we need to be because we need to figure out how many grams of iron 2 oxide I need. And so that brings us to the next conversion factor. Let me clear my mess up right here, which now, keeping track of my units, grams of aluminum cancel, moles of aluminum cancel, moles of iron 2 oxide cancel, leaving me with units of grams of iron 2 oxide, which is what the question asks. So now it's a matter of plugging in the numbers in your calculator and keeping track of your sig figs. You got 3 sig figs, 5.55, which is a measurement. Okay, all the other units in there, the conversion factors are not do not play a role in sig figs. Okay, so that means that if I start off in the lab with 5.5 grams of aluminum, I need to weigh out 22.2 grams of iron 2 oxide, okay, to get this reaction to proceed with the proper ratios. Okay. The next one was we were calculating starting with aluminum. What was it? We're going from aluminum to aluminum oxide. Almost forgot which direction we're going. All right, so we're starting with aluminum, and we need to figure out how much aluminum oxide we're going to make. Okay, so like we did before, step number one, take the grams of what you were given and convert it to moles. In this case, we're going to use the atomic weight of aluminum again. Okay, that will give us moles of aluminum. Then we look at the balance chemical equation, look at the stoichiometric relationship between the aluminum oxide and aluminum, and it's a 1:2. Okay. I can't overemphasize, we're not concerned about everybody else in the chemical reaction. Our only concern is what that question asks us to do our calculations from, and that is from aluminum and aluminum oxide. So at this point, as you go along, you're keeping track of your units, you are now in units of moles of aluminum oxide. You see how you went from bananas to oranges? Okay. But you got one more step, because the question asks you to put it into grams of aluminum oxide. And to do that, we need the molar mass for aluminum oxide. So we've got 2 aluminums, 3 oxygens. That gives us a total of 101.96 grams per mole. Okay. Check your units, making sure you got them set up properly and everything's canceled out. And so now, plug in your numbers in the calculator, you should come up with 19.37 grams of aluminum oxide. Okay, so to rehash, if I start off with 10.25 grams of aluminum, and I got plenty of iron 2 oxide involved there, I will generate 19.37 grams of aluminum oxide. And that's assuming that you make 100%. But in reality, when you get into the lab, no reaction is 100%. And after you go through the process of isolating, you might isolate, half of that material, and you actually calculate the actual amount you isolated divided by the theoretical amount that you can make, which is in this case 19.37, and multiply that by 100, it gives you a percentage. So the actual yield divided by the calculated yield times 100 gives you a percent yield. And you strive to get to 100%, but very rarely do you, in a real reaction, do you actually get close to 100%. And if you get over 100%, then that means you created matter, and that's not the case. It generally means that your material needs to be cleaned up a little bit more. All right. Okay, so here's the flow chart. Okay, that combines all of the points of going from point A to point B, and that includes those points where you are at STP written in yellow. Okay, and so as I stated, if you are in grams and you need to get to grams of whatever you're looking for, you cannot do that directly. You have to go through moles. Okay, and so the first step is, given the grams of your starting material, you need the molar mass. From the molar mass, it gives you the moles. Now at this point, depending on where you need to go, if I'm going to figure out the volume of that material given, and then I have to be at SDP here, so I can calculate the volume of that material, okay? But sometimes I don't need to do that. I need to go to find the grams of whatever I'm looking for. So I need the mole ratio, which comes from the balanced chemical equation. And that tells me how many moles I'm looking for. That's the moles of what I'm looking for. And then at this point, depending on what the question is, I can go to grams if I multiply it by the molar mass, or I can figure out a volume if it is at STP using this relationship, okay? Now let me clear my mess up. So there's a multiple ways to go here, and it all depends on the question, okay? I mean, we can start off as a gas, and we need to go to grams. Okay, I mean, we can start off over here and going through this process, figure out the grams, okay? Or we can start off in the bottom left corner and go that direction if necessary to get the product in volume if we're at SDP, okay? And any other combination, not just the one way, is really like a two-way arrow that we should put here. But the point is this flow chart can direct you how to go about and calculate the problems that you need to calculate, okay? By identifying what you're given and what you're looking for and having a balanced chemical equation, okay? So, like I stated, a typical type of problem given is you're given a reaction in words. From the words, you convert that to a chemical reaction with the formula, okay? From that, you balance it. And then from there, you do your calculations. All right. So, for example, here's a classic example. Write and balance the reaction of hydrochloric acid and cobalt, okay? So let's first write down this reaction. So we have cobalt. Oh, let me change the color here. So we have cobalt solid plus HCl. Now, can anybody tell me what type of reaction this is? Which will help you to identify what the products will be. Anybody have any idea? I'll give you another hint. Activity series. Does that help? Yes, there you go. It is a single replacement reaction because remember in the activity series, it was a relative scale relative to hydrogen gas, okay? And hydrogen, the ionic form of hydrogen was H+, or obviously the elemental form is hydrogen. So here we use the activity series and we look up cobalt versus hydrogen, and we'll see that cobalt is a lot more reactive than hydrogen. Therefore, this reaction will proceed because cobalt is not in ionic form. Plus, they're telling you here that cobalt will be in the +2 state at the other end of the reaction as a product. So we're going to make hydrogen gas, okay, because we're replacing the metal with the hydrogen. And then we're going to have the other we know we got chloride, which is a -1, and the cobalt, which is a +2, because we're telling you, and we have to tell you that because remember, cobalt is one of the metals has a variable oxidation state. So you have to be told that information. If this was something else like magnesium or aluminum, we don't have to tell you why, because we know that those metals, we know their oxidation state. So that means we need two chlorides for every cobalt. So we have cobalt, Cl2, and if you look up the solubility rules, okay, you'll see that this is soluble. Cobalt 2 chloride is soluble because the halides are soluble, so that'd be AQ. Okay, so how everything's all tied together, the elements, and what their charges are, and so forth. All right, now we balance. All right, so we have two chlorides on the right, one on the left. All right, so what if we put a 2 in front of HCl? That will balance the chlorides, okay? It also balances the hydrogens, and then the cobalts are already balanced with 1. So we have a balanced chemical equation. Okay, and so let me erase something here. You can erase this. All right. So we got it balanced, I believe. Double check me. I think everything's correct. All the physical states are there. Yep. All right, let me clear this up. My mess. All right, now the question is, how many liters at STP will form if 5.0 grams of cobalt reacts? Okay, so we're going to identify who we're working with here. How many liters of gas? Okay, so kind of a tricky question, but not really, because how many liters of gas will form? So it's a gas in the product side. Well, they obviously the only gas there is hydrogen. So we need to know how many liters of that. If you have 5 grams of cobalt, so our concern is the relationship between cobalt and hydrogen. Okay. All right. So what we do is we write down what we're given. We got 5 grams of cobalt. Okay. We need to figure out its moles of cobalt, which is, what's that number in front of me? 58.93 grams in 1 mole. Okay. And that puts us in moles of cobalt. Okay. And so let me back it up a little bit. We are going from the far left corner to the left, bottom left volume. We're going from grams given to volume. Okay. All right. And so our next step is, let me erase my mess. It gives us the moles of cobalt, okay? Then the fact that it's a 1-to-1 relationship between cobalt and the gas is a 1-to-1, okay? So that now puts us in units of moles of hydrogen. So we went from grams of cobalt to moles of cobalt to now we are in moles of hydrogen, okay? And since we are at STP, we can use the 22.4 liter per mole relationship because the question is asking us to get to grams, excuse me, liters of hydrogen gas. And so we plug that in and we end up with 1.9, almost 2 liters of hydrogen gas are created if you start off with 5 grams of cobalt, 1.90 to be exact. Okay, and so let me clarify. We are going back to the flow chart. We are here. We were given moles ratios, moles fine, volume fine. So we went in this direction. Okay, I was directing you here to the bottom left, my mistake. Okay. All right. Now, the other question is, second part of the question, if 2.374 liters of hydrogen gas are formed, how many grams of hydrochloric acid were reacted? And so we're looking at HCl and hydrogen. Okay. And so the first is 2.374 liters of hydrogen. We're still at STP. So we can convert that volume to moles of hydrogen, being at STP. Both of these problems couldn't be done the way we did them if we were not at STP. Okay, so that gives us moles of hydrogen. Okay, from the stoichiometric relationship between HCl and hydrogen, it's a 2-to-1 ratio. And so now we are in moles of hydrochloric acid, HCl. Now using the atomic mass, the molar mass of HCl, okay, which is 35.46 for hydrogen and 1.01 for, chloride and hydrogen, it's 36.46 grams per mole. Okay, so check my units, make sure I set this up properly. And you can see liters cancel out, moles H2 cancel out, moles of HCl cancel, leaving us with grams of HCl, which is what we're looking for. Okay, and so now our answer is 7.73 grams HCl. Now, note carefully here that with respect to sig figs, we have 3 sig figs in the answer, right? Now, the 2 and the 1 are exact, and atomic weights are not utilized for sig fig purposes, but we have 4 over here to begin with, which is a measurement. But remember, I said that the 22.4 liter is a measurement, so it could be a factor when you use it with respect to sig figs. In this case, it does play a factor. So 22.4 has 3 sig figs. Our answer should be no more accurate than 3 sig figs. Okay. All right. There's another one. It says here we got a word problem. We're going to convert it to a reaction. HCl gas, hydrogen chloride, plus oxygen, O2, which are gases, produce, which is my arrow, chlorine gas, keyword chlorine gas, which is the diatomic, okay, plus water vapor, H2O. Okay. So now need to balance it. All right. So we got Well, let's see, we got two hydrogens on the right, one on the left. What if I put a 2 in front of HCl? That balances out my hydrogen. Okay. That also takes care of my hydrogens and my chlorides, but my oxygens get a little bit whacked out, right? So what if I put a 2 in front of my H2O that takes care of my oxygens, but that kicked up my hydrogens to 4, right? And then that kicks up my chloride. So what if I put a 2 in front of Cl2? Let's check. 4 hydrogens on the left, 4 on the right. 4 chloride, Cl's on the left, 4 on the right. 2 oxygens on the left, 2 on the right. Okay, that looks balanced. Okay, here we go. Now, how many liters of chlorine can be formed if 3 liters of oxygen react completely at STP? So we're looking at chlorine and oxygen. Okay. All right. So we write down what we're given: 3.00 liters of oxygen. Okay. We are at STP. So we can use that relationship of 1 mole per 22.4 liters. Then our stoichiometric relationship is a 2-to-1 because we're concerned only about the oxygen and the chlorine. And then that puts us in moles of chlorine, which now we want to get to volume of chlorine, which then we use the 22.4 liter again. And that turns out to be 6 liters of chlorine. Now, notice something interesting here. You can go directly to, if you are at STP, okay, and your reactants and products are in the gas phase, you can simply use the stoichiometric relationship directly to get to the answer. Why is that? Because note this, the first 22.4 liters converts the first liters to moles, right? Then at the end, you got to use it again to cancel it out. But they cancel each other out, don't they? So all you have to really worry about is the stoichiometric relationship in between the two, right? But if you don't see it, don't worry about it. Go ahead and put the 22.4 before and after, and keep track of your units. But you'll see, and the more practice you have with these type of problems, you can go directly to the answer. It's simply based on the stoichiometric relationship in the balanced chemical equation. Okay. All right. All right, try these at home. Where we have carbon reacts with oxygen to form carbon monoxide. How many liters of carbon monoxide STP can be made from 15 grams of carbon? Well, let's try these. We got time right now. Let's try the first one. I'll let you have the second. You can try the second one at home. Because the first one says, how many liters of carbon monoxide STP can be made from 15 grams of carbon? And then the second part says, how many liters of carbon monoxide at STP can be made from 20 liters of oxygen gas? All right, so let's do the first part, given the time that we have. It says carbon reacts with oxygen to form carbon monoxide. Well, let's write the equation. Carbon reacts with oxygen to form carbon monoxide. Okay. All right, so let's balance it out. Well, what if we put a 2 in front of carbon monoxide? That balances out the oxygens, and then we need a 2 in front of carbon, correct? So we all balance out. We know that carbon is solid, oxygen is a gas, carbon monoxide would be a gas also. Okay, does that look balanced? All right, now we're still at STP, so keep that in mind so we can utilize a 22.4 liter per mole relationship. And we want to know how many liters of carbon monoxide are made from 15 grams of carbon. So that's our relationship between carbon and carbon monoxide, which is a 2-to-2 or 1-to-1 relationship. So 15.0 grams of carbon. Okay, we need to get to moles of carbon. So we know that 1 mole of carbon is 12.01 grams. Okay, the atomic weight. So that gets us into moles of carbon. We need to get to oxygen. All right, so our stoichiometric relationship, not carbon, but carbon monoxide. What am I saying? Moles of carbon monoxide. So that relationship is a 2-to-2 based on the balanced chemical equation. So carbons cancel. We are in units of moles of carbon monoxide. Okay. And since we are at STP, we can use a 22.4 liters per 1 mole. Okay, that cancels out the carbon monoxide, and we can convert that to liters now. So let's double check. We're looking, we've got the balanced chemical equation. Okay, taking that from what we read, we balanced it out. Then we identify what the question is asking us. We want to know if we start off with 15 grams of carbon, how many liters of carbon monoxide do we make? Okay, so then I had to take the grams of carbon that we have, convert it to moles of carbon by dividing it by the atomic weight of carbon. Then from a stoichiometric relationship of carbon monoxide and carbon, that converts us to moles of carbon monoxide. And since we are at STP, we can then utilize the 22.4 liters per mole. And then once you do the math, you should come up with the answer, right? And you should come up with 28.0 liters of carbon monoxide. I guess you got the answer at the other one too, but the other one you end up with 40 liters of carbon monoxide. All right. All right, so the takeaway from this whole chapter is as follows. 1, if I need to get from grams of A to grams of B, whether it's the reactants with each other or the reactants and the products, what I need to do is I need to convert first into moles, okay? And I take the grams I'm given, divided by the molar mass, which will give me the moles of what I'm given. Then from the mole ratio, I can determine the moles that I'm looking for, what the problem asks for, and then for moles of B, okay? So I start off with grams of A divided by the molar mass of A, that gives me the moles of A. From the stoichiometric relationship of the balanced chemical reaction, the mole ratio, I now get into moles of B. And from its molar mass, I get grams of B, okay? So I go from A to B, grams of A to grams of B through moles. And if I'm at STP, 0 degrees and 1 atmosphere, then I can use that relationship of 22.4 liters per mole So I can go directly into the volume of gas. Either I'm given the gas, I can get from the gas to moles, or if I have the moles of gas, I can get to the volume. Okay, but use this flow chart. This flow chart is very helpful in figuring out what direction, because I know sometimes based on the problem that you're given, it can be like, wow, you're overwhelmed with what you're trying to calculate, but break it down, write the equation out, mark where you're at and where you're going on the equation, what you're given, what you're looking for, and then use the flow chart to guide you through the correct steps to get you to where you need to be. Okay. All right. See how short this chapter is? Congratulations, you are done with chapter 13. And be sure to work through the worksheets. Okay, there's some examples of problems, and if there are any